So inverse of a square matrix is denoted by A inverse, same notation as we've seen before. And when you multiply something by its inverse, you get 1. Sort of the same idea that things cancel each other out, dividing and multiplying, square rooting and squaring, things that are inverses. When you multiply something by its inverse, you get an identity matrix, which is basically the number 1 of matrices. How do you find an inverse? Well, here's the formula for the inverse of a 2 by 2 matrix. Notice it has the determinant in it as a scalar multiple in front, 1 over the determinant of A. And so earlier we had said that if the determinant's equal to 0, there is no inverse, and this is the reason why. If the determinant's 0, you'd be dividing by 0. Dividing by 0 is not allowed. And so for the inverse, the determinant cannot be equal to 0. Next, some very interesting applications happen. Notice the inverse, 1 over the determinant. Then the A and the D get switched, and the B and the C are multiplied by a negative. Just for fun. So if we were just calculating this out using the formula, we could say, let's say I call this matrix A, then the determinant of matrix A would be 6 minus 5, which is 1. And the inverse of matrix A would equal, the inverse of matrix A would be 1 over the determinant, 1 over 1. Switch this diagonal and make the other diagonal negative. Now notice, if we multiply matrix A times the inverse, so matrix A, 2, 1, 5, 3, and the inverse, 3, negative 1, negative 5, 2. We notice that this is possible because this is a 2 by 2 and this is a 2 by 2. The middle numbers match up. Your answer should be also the outside numbers, a 2 by 2. If I want to find the number in the first section, row 1, column 1, I would take row 1, turn it on its side, multiply it by column 1. You see that you would get 6 and minus 5. Added together will be 1. If I want to take row 1 and column 2, now I'll get negative 2 and positive 2. I will get 0. Row 2, column 1, 15 and minus 15, 0. And row 2 and column 2, negative 5 and 6, 1. So if you want to check if your inverse is correct, you can put it into your calculator, multiply them together, and find it out. Does your calculator have an inverse button? So let's write in this matrix and see if we can find out if we can calculate it with our calculator. So matrix A was 2, 1, 5, 3. I'll store that as matrix A. Now, if you go to matrices and math, notice that there was no inverse listed there. However, on your calculator, there's this little x to the minus 1 button. See if that works. And it does. Very nice. So if we look at our second example, can you see the determinant? If I call this matrix B, that the determinant of matrix B would be 3. So B inverse would be 1/3. Flip these two, multiply each of those by a negative. And you can leave that 1/3 out in front, or if you wanted to, you could put that 1/3 in as a scalar. So you could write negative 1/3, negative 2/3, 0, and negative 1 if you multiply through by that negative. So again, here's this explanation. Because you have to divide by your determinant can't be equal to 0. So a singular matrix has no inverse. What's that? You're multiplying by a scalar there. You're multiplying by a fraction, not dividing. Okay, for our 3x3s, there is a nice long-winded way to find a determinant or the inverse of a 3x3 without a calculator. It is not pretty. So for 3x3s, we will use our calculator to find it. So type this one in. Into your calculator. Push enter, push F inverse, get the value, see if you get the same answer that I did. So now we're going to find out how we can do something we already know how to do in a different way using matrices. Now, you already know how to solve this system of equations. You can solve this system of equations with elimination. I'd probably take this equation and subtract this equation, which would give me 0 here. Negative 2 minus a negative y would give me negative y. Negative 2 minus a negative 11 would give me plus 9. So y is equal to negative 9. And once I know that y is equal to negative 9, I can plug it into either of these equations and solve for x. And it looks like x is equal to negative 5. Does that work? Negative 20 plus 18, yes. Negative 20 plus 9, yes. So our old system works really well for solving for this. How can we use our new system with matrices? Well, once we do the initial part, you probably go, I still like the old system for how fast it is. But as we get into bigger equations, it might be nice to write them as matrices. So I can write the above systems of equations using matrix multiplication. I have a coefficients matrix, I have a variables matrix, and I have a constants or my answers matrix. First of all, can you see that if I took the first two matrices, this is a 2 by 2, and this is a 2 by 1, that you could multiply them? And if you multiplied them together, you would get a 2 by 1, and you would get 4x minus 2y for your first one, and you would get 4x minus y for your second one, which is exactly the equations we had to start with. So we first recognize that what we've written with matrices is identical to what we started with. Now, using your inverse, what you basically have is a matrix A times your variable matrix equal to a matrix B. If I want to get rid of that matrix A in front, just to get my variables by themselves, I would have to multiply by A inverse. And this is where matrices add a little bit of complication. So we're multiplying one side by A inverse, we multiply the other side by A inverse. But since matrices, it matters the order in how you multiply things. If you multiply by A inverse in the front on this side, it has to be in the front on that side. And that's going to be important because if you think about matrix B, it was a 2 by 1. If I put A inverse on the other side, the middle numbers don't match up. So it only works if you have the A inverse in the front. And so if you multiply on the front on one side, you have to multiply by the front on the other side. Now, A inverse times A will just be your identity matrix, and your identity matrix acts like the number 1. Anything multiplied by an identity matrix is itself. So that means on the left-hand side, we just get x. And on the right-hand side, we have A inverse times B. So if we look at the question we just had, this as a matrix equation would be 4, negative 2, 4, negative 1. Now, the inverse of matrix A, if I multiplied this side in front by A inverse, I would have to multiply this side in front by A inverse. The left-hand side will then just become xy. The right-hand side, well, my determinant will be negative 4 minus a negative 8, which will be positive 4 for the determinant. Switch these two. Switch the signs on these two. There's my inverse. Multiplied by negative 2 and negative 11. Now, personally, I like to keep that fraction of 1/4 out in front. If I would take these two matrices and multiply them, I have a 2 by 2 multiplied by a 2 by 1. My answer will be a 2 by 1. Row 1 times column 1 will be 2 minus 22 minus 20. Row 2 by column 2 will be 8 minus 44 minus 36. And now if I multiply through by that 1/4, I get negative 5, 9. So this tells us that x is negative 5 and y is negative 9. Now, for 2 reasons, you should agree that our elimination technique that we did at the beginning was better. 1, it was faster. And 2, you're more familiar with it. So you will always pick what you're more familiar with as a method that I like better as compared to something that's new. But in this case, this was more work than the other method, and because it's new, it probably has a little bit less meaning as well. It's a little bit more abstract. But it is neat that it comes out to give us the same answer. So let's do a couple more using matrices. Set up our coefficients matrix, our variables matrix, our answer matrix. I mean, technically, we haven't defined what A is, so I haven't defined what A inverse is. Some technical places, like an IB math course, might get mad at you for something like that. At this point, I'm okay with it. Are you, like, just for generality, I put that there. Now we know that this side will just become xy. To find the inverse, we need the determinant. This is 3. This is minus 2. 3 minus a negative 2 will be 5. So the determinant is 5, so we'll have a 1/5. Switch these two, change the sign on these two, and we have our inverse multiplied by 5, 0. Again, I keep that 1/5. If I multiply these through, 1, 2 times 5, 0 will just be 5. Negative 1, 3 times 5, 0 will be negative 5. And we find out that x has to be 1 and y has to be negative 1. Do a quick check. Anytime I'm solving an equation like this, I like to go back to my original equation and check. If I plug in 1, 3 minus, and I plug in negative 1, a negative 2, that makes 5. 1 plus negative 1, that makes 0. It works. Whew. Not the nicest equation. I would rearrange here. I would probably take equation 2, multiply both sides by 4, and move the 3x over. So I've taken equation 2 and done some rearranging. Now that I've rearranged it, I can write my coefficients matrix, 1, 1, negative 3, 4, times my variables matrix, equal to 1, and now it's negative 31. Yes? Yes. It has to be, because if you think about when I take this and I multiply it by this, I need to get that equation. So it turns on its side. The negative 3 has to hit the x. The 4 has to hit the y. So we're seeing another application of that matrix multiplication and why the order matters there. No. You can switch your, like, having negative 3 and 4 on the top as long as it corresponds to the negative 31. Right? If you had negative 31 on top, that's fine. So what Ted's asking, could I have this equation first? Absolutely, as long as it matches with the answer being first as well. So now I can multiply again the front of this one by the inverse, the front of this one by the inverse. And we would get matrix xy equals, the inverse here, 4 minus a negative 3 will be 1/7. Switch them, switch the signs. Again, keep that fraction out until the end, unless you really love multiplying by fractions and adding fractions. Multiply and add, so I get 35 up there. Multiply and add, negative 28. You can if you want, but it's in a matrix question, it's implied from that answer. Yeah. You're going to leave it like that. You know that x is equal to 5 and y is equal to negative 4. Now, just show you some things on your calculator that can kind of be a little bit of fun for this one. I'm going to just go. So on your calculator, what I'd like you to do is I'd like you to make a matrix, so alpha, and you're going to make this matrix with 2 rows and 3 columns. And in this matrix with 2 rows and 3 columns, I'm going to write 1, 1, 1. Oh. Try that again. 1 arrow, 1, 1, and negative 3, 4, and negative 31. I'm going to take that and store that as matrix, nope, second matrix A. And then go to matrix and go to math. And that one that I said you were really going to like, the reduced row echelon form of matrix A. And what it will do is it will rewrite these equations. Here, we'll show you the answer. With an identity matrix there, and a 5 and a negative 4. So this says 1x plus 0y's is equal to 5, and 0x's plus 1y is equal to negative 4. Which is really nice because that is our solution. Of course, in this course, we're going to have to learn how to do that by hand. but we'll be able to see it and how to do that as well. Yes. So if you had a 3x3 system of equations, you could make what we made originally. And sometimes when we're writing them out, so I made this matrix like this, and then I made this matrix like this. Sometimes you'll see in text or textbooks, or maybe this is my own thing that I like to do. I like to draw a line there, so it's sort of like this was my original equation, these were my answers, that line is kind of like my equal sign. And this is called an augmented matrix. In an augmented matrix, you can always, if an inverse exists, put it in a reduced row echelon form where there's a 1 here, 0, 0, and 1, basically an identity matrix in one place and answers on the other place, and what you get is a solution. So if we go back to our matrices, let's go second alpha. Let's create a system of 3 equations. And do you want to make a nice one? Let's make a nice one to start with. Okay? So I'm going to make a 3x4 system of equation. Do you know how you make a nice systems of equations question? You think of the answers beforehand. So what do you want x to be? 4. Okay, you can pick y. 1. And z? -7 over, no, we want to make nice equations. 9. Okay? 9. So would you agree that x plus y plus z is 14? Okay, and then we could take 2x plus y minus z, that would be 0. And what else would we like? We'd like 3x's minus y minus 2z would be what? Three x's, 12, 11, minus 18, -7. So we know the answer to this is 4, 1, 9. It is easier to make them. And then this is what a teacher does. They go, ooh, your turn. Right? And they're like, oh. And then it appears like I can do it quickly in my head, but I made it to begin with the numbers. But what we have here, so we can go to our calculator. We have, there we go, calculators appeared. So we had 1, oh, I did it again. 1 over 1 over 1 was 14. And then the next one was 2, 1, -1. 2, 1, -1. That one was 0. And the last one was 2, -1, 3, -1, -2. I know, I could. -2, -7. Enter. Store it as matrix A. And now do our matrix math with that one. Reduced row echelon form of matrix A. Alpha math has it too? Look at that. 419. Matrix over. Alpha apps here. Oh. Oh, because it's listed as letter B. If you'd remembered that. So now let's make one that wouldn't necessarily be pretty. Okay, so, all right, okay, here we go. We're going to go alpha. We're going to make it 3 by 4. Pick some numbers. I'll go pi. You want E? And 3. 20. We don't want to. 6, 3, 3, 3. You want log of 6? Natural log of 12? And now we have to make sure we have that negative 7 on 3. And 13. Oh. That is important. There we go. Now, if you had a systems of equations of this by hand, it would not be fun for eliminating variables. But if we, wow, look, they nicely changed it to decimals for us. We'll store this as matrix A. Reduced row echelon form of matrix A. Apparently, those are the answers. Yeah. I guessed 20 for the second one, but it looks like I was just a little bit off. Easy. Easy to write out.